Welcome viewers. In this video we are going to do design of a stub and cleat using American Standard ASCE for transmission line tower foundation. So for design of a stub, as we already discussed, these are the steps to be included for checking the stub stability and the design of the member, cleat and bolt. So first step is to check for embedment, combined tension and check shear check, combined compression and shear check, bolt design, cleat angle design, compressive stress in concrete. These are the steps, 6 number of steps to be involved in design of stub. Let me look into that calculation part. On the screen you can able to see an Excel sheet which we are going to do the design of stub and cleat. First we need to define the material parameters. In that material parameters we are having two categories of materials. One is high strength steel, another one is mild steel. So these material parameters used to define based upon the technical requirement of the project or the contract agreement. The standards to be followed for this high strength steel is ASTM A572M, and for mild steel it is ASTM A36M. Yield strength for high strength steel is 345 megapascal, which is equal to 50 kilo pound square inch. Similar like for mild steel it is 250 megapascal equivalent to 36 kilo pound square inch. Tensile strength is 448 megapascal equivalent to 65 kilo pound square inch for high strength steel. For mild steel it is 400 megapascal equivalent to 58 kilo pound square inch. Diameter, minimum diameter of the bolt we can consider as a 16 mm, which is 5 by 8 inches. This is as per ASTM A394. Tensile strength of the bolt is 510 megapascal, which is equal to 74 kilo pound square inch. Shear strength of the bolt is 310 megapascal, which is equal to 45 kilo pound square inch. Next we need to feed the loadings. So these are the loads we had extract from the structure model, which we had already discussed in our last video. So these are the input like a compression, tension, shear in transverse and longitudinal directions. So these are the input from the structure model. And resultant shear is nothing but it is a square root of squares of transverse and longitudinal direction forces. Here that minimum yield stress of stub and cleat angle are taken from this table, which are from the technical specification. Similar like the bolt, bearing and shear stress. A tensile stress is considered from the main stub. Characteristic strength of concrete we can assume here as a 25 megapascal. Coming to the section properties, the main stub of member section is generally equal to main leg of the structure, or in case of any extension of body extensions or leg extension, we can consider the leg size which we are going to consider for the extension. So here we can consider the same as per the bottom leg, 150 by 150 by 15 angle. Cleat and angle member we can assume there is a 4 number of cleat angle to be bolted with the stub. The angle size is 120 by 12. Length of the cleat angle you can assume now as 130 mm. Number of bolts also is 4 numbers. Diameter of the bolt is 16 mm we can assume here now. And cross area of the bolt is by d square by 4, where d is 16 mm. Diameter of the holes in stub for bolt we can consider 1.5 mm extra to the diameter of the bolt, so that this hole can be able to accommodate the 16 mm diameter. Spacing between bolts is 2.5 times the diameter of the bolt. Cross area of the stub we can pick from the table which are listed here. So using this vlook command and a drop down list to pick this input of main stack member section, this cross area stub angle can be extract from the table which is in the next tab. Net area of a stub angle is nothing but it is a deduction of cross area of stub angle with the stress area. Actually this net area is nothing but it is a stress area. In that we need to deduct that 2 times the thickness of the stub with the and the hole diameter. So here the hole diameter is 17.5, that into 15 is the thickness of the main leg member. So 2 times that should be deducted from this net area. So that the net area of a stub angle is 3775. Root radius for cleat member we can pick from here in this table by using the drop down list and the VLOOKUP equations. Then the next step of design of stub and angle is check for stress in stub angle. There are two types of check to be done for stub angle. One is combined compression and shear strength. Another one is combined tension and shear strength. In that actual compression strength is C divided by AG. C is nothing but it is a compressive force which we got calculated in the structure modeling. And gross area is 4300 square mm, which is for stub angle. Actual shear strength is S divided by A net. S is nothing but it is a resultant shear which is extracted from the structure. And the net area of stub angle is 3775, which we had calculated just above. Shear resistance, generally we used to consider 40 to 60% of yield strength of steel as a shear resistance. Here we can consider as a conservative side as 0.4, that is 40%. So it is 0.4 into yield strength of stub steel is 345. So it is 138 megapascal. Now we need to calculate the combined tension and shear strength usage factor. So that is nothing but it is actual compression divided by yield strength of steel plus actual shear strength divided by the shear resistance. So it is coming 61%, then we can call it as safe, because anything more than this usage factor greater than 1 or 100%, it is unsafe. So next one is combined tension and shear strength we need to check. In that actual tensile strength is U divided by AG. U is nothing but uplift force which we had extracted from the structure. And as usual the gross area of stub is 4300. Actual shear strength is the same as like we calculated in combined compression and shear strength, which is 33 megapascal. And in this shear, in this we need to consider strength reduction factor as per class D4 of 4 Annex D ASCE 31805. For that page number 389 to be referred. So this is a code and the class which I am showing in that PDF file. So here the tension load we need to consider 0.75, and for shear loads we need to consider 0.65 for angle governed by strength of a ductile steel element. So that's why we are considering here 0.75 for tensile resistance factor, and shear resistance factor it is 0.65. Finally, we need to calculate the reduced tensile strength, that is yield strength, into the 0.75, the reduction factor. So it is 259 megapascal. Similarly, like for shear strength to be calculated, the shear resistance into the factor which is considered here 0.65. So the value is 90 megapascal. Again, here the same method of calculating the usage for combined tension and shear strength. It is nothing but the actual tensile strength divided by the reduced tensile strength plus actual shear strength divided by the reduced shear strength 90 megapascal. So by applying this we are getting 94%, which is to be seems to be as a safe. If this 94% is nearer to the margin of 100% of utilization, we can change here the higher section so that this will get reduced. For our calculation purpose, we can consider as it is the main leg of the tower structure, that is 150 by 150 by 15, even though there is a marginal usage factor 94%. So these are the two parameters we need to do for stub angle strength check. Next, we are going to check the bolt strength. So in this, we are going to check two parameters. One is bearing, bolt check on bearing, bolt check in shear. Maximum axial force, we need to consider maximum of tension or compression. So maximum of these two we need to consider for the calculation of bearing check. Force per cleat, here you can see force per cleat is nothing but the maximum axial force, that is compression or uplift, divided by the number of cleat which you are providing. In this two cleat only we need to consider. 2 means that 50% number of cleat which we had considered as a section properties to be considered. Why it is? Because you can see in the picture there are some 6 cleats are there. In that two side 3, another side it is 3. It means whenever we are considering the 4 cleat, only 2 will come one side of the main stub, and another direction which is perpendicular to the flange which is fixed in one direction, there are another 2. So only 50% of numbers will effectively act in one side for axial forces. So here we need to consider only the 50% of number of cleat which are connected in the stub. So it means 4 divided by 2, only 2 numbers of cleat we need to consider. So force per cleat will be the 318.05 kilonewton. Force per bolt, here we already consider 4 number of bolt per cleat to connect with the stub. So divided by 4, it is 79.52 kilonewton. So in the picture also you can see there are 4 bolts are connected to the stub with the cleat. Bearing area is nothing but diameter of the bolt into thickness of the stub, so which is 16 into 15. Actually in this we need to connect only the least thickness of members which are connecting here compared to the cleat and the main stub. Only the cleat angle is having the least thickness, which is 12. So we need to select the least thickness only. So this should be thickness of cleat TC. So it is 192 square mm. So next is we need to find the calculated bearing stress, which is nothing but the force per bolt divided by the bearing area TB into TC, which is coming 414 megapascal, which is less than the 510 megapascal, which is the bearing stress limit of bolt. Hence we can call it as a safe. So this is also coming in marginal 81%. Next one, check for shear. So here the maximum shear force again is maximum of compression or uplift. Force per cleat, here all the forces will act like shear member, all the cleat member. So we need to consider the total entire 4 numbers of cleat. Force, that is shear force per bolt, is nothing but the VC, that is maximum force per cleat divided by the 4 numbers of bolt which we got considered to connect the cleat with the stub. And the calculated shear stress is nothing but VB divided by gross area of bolt. So gross area of bolt is pi d square by 4, where the d is 16 mm. It is 201 square mm. So that we need to divide it by VB. So we are getting 198 megapascal, which is less than 310 megapascal, which is the shear stress of bolt, shear carrying capacity of bolt. Hence it is safe, but here the usage factor is 64%. So these two parameters are stating that the bolt arrangement which we got provided, that is 4 numbers of bolt of 16 dia, is safe to hold this force, the structure force, through the stub. Next step for this design of stub and cleat is check for compressive strength in concrete. This is relevant to the cleat angle. For that compressive stress we need to calculate. The compressive stress is nothing but C, which is a compressive force from the tower, that into 1000 to convert kilonewton into Newton, divided by the number of cleat which we had considered is 4, and SC is nothing but it is a size, that is a cross-sectional or flange size of the cleat angle which we got selected is L 120 by 12. In this 120 is a side span or width of the cleat. So 120 into the length of the cleat member we have considered is 130 mm. So by applying all this value in this formula, C into 1000 divided by NC, SC and LC, we are getting 8.89 megapascal as a compressive strength. So already we know that compressive strength of concrete which we had considered for this foundation or the pedestal is 25 megapascal, which is higher than the 8.89 actual compressive stress. So hence it is safe. The usage factor is 8.89 divided by 25 equal to 0.36, which is a 36% of usage. Hence it is safe. So this is a check for compressive strength of concrete where the force is transferred. So here in the picture you can see there are some 6 number of cleat, but in our calculation we can consider only the 4 number of cleat here. So in upcoming calculation of the steps like check for capacity of angle shear connectors, we will get more clear about how much number of cleat is required. But in this we can see there are four number of bolt are connected here. So we have considered the 4 number of bolts which is safe, and the length here which we had considered LC as 130 mm is nothing but it is the length of every cleat. So this is the length in cleat of this direction, which is viewer side, and in the cross sectional side there are 3 number of cleat. So the length is the other side we need to check. So the length and the bolt and even the cleat size also safe. So far we had checked. Now next we are going to go to the next step, that is the 7th step, check for capacity of angle shear connectors. In this check we need to do the bending stress of the angle connectors. Bending stress is 1.19 into FC. FC is a characteristic strength of concrete. This we can refer to class C762 of ASCE 1097. So you can see that code which is showing here. This is a code to be considered for designing the lattice steel transmission tower. So as per the requirement we need to check the page number 58. So here it is given the values obtained in equation 7.5.2 are based on initial yielding of angle strength at a stress of 1.19 FC in the concrete. So we need to multiply this 1.19 with the characteristic strength 25 megapascal which we had considered, and this X is a lever arm distance. You can show in the picture here. the lever arm distance, which is start from the distance of r plus t. R is the root radius and t is the thickness of cleat angle. So from there it is going to start this x distance up to the pressure diagram, which is showing here, where the pressure diagram is meet 0. That distance is called as x. So this equation to find this x value is given in page 36 of ASCE 10. So here you can see the equation is given x equal to t into Fy divided by 1.19 Fc whole square root, which should be lesser than or equal to W minus R minus T. So in that we can consider a minimum of T into square root of Fy divided by 1.19 Fc and W minus R minus T as per the code equation under 7.6.2 class. So by applying this, we are getting x value as 34.79. It means the zero pressure distribution starting point from the r plus t distance. R is a root radius and t is the thickness of cleat angle member. So this is a x distance which is showing in the picture. So at this x distance only the pressure, the vertical load is used to act, the pressure load used to act. So that load capacity we need to calculate it from the equation which is showing in the 7.6.2 of ASCE 1097. P equal to 1.19 FCP into T plus R plus X by 2. So T is the thickness of the cleat angle, R is the root radius, and P is the length of the cleat angle or shear connector. So here those definitions are given here. So by applying this formula, we can able to find out the cleat load capacity. So this as per the equation given here under class 7.6.2. So we know that 1.19 Fc equal to 29.75 megapascal multiplied by length is the 130 mm, which we can consider here as a length of cleat member, and T we know that root radius, T is the thickness of the cleat angle 12 mm, root radius we know that it is 13 mm from the table which is extracted, and x divided by 2 is already calculated as 34.79. By applying all these values, and also the number of cleats we know that it is 4 numbers we had considered here. So the load carrying capacity of the cleat arrangement is coming 655.86 kilonewton as per our calculation. The calculated or the structure value we can consider as maximum of compression or uplift, which is 636.09 kilonewton, which is less than 655.86, which is a load bearing capacity of the entire cleat arrangement. So we can call it as safe, but the usage factor, if you look into that, it is having a 97%, which is really a marginal amount, which is nearer to very close to 100%. So either we can increase the number of cleat by reducing this. So what we can do is we can consider as 6 numbers here as in the picture in the right hand side. So there are 6 number of cleats with the 4 number of bolted connected to stub. So by changing this load bearing capacity is coming to utilization as usage factor as a 0.65 or usage percentage as a 65%. So it became more safe compared to earlier. So we can have it as a 6 number of cleat with the 4 number of bolts of M16 connected to stub angle as our design requirement. And then next we need to check that the combined tension and shear which is occurred at the bottom of the cleat. So for that we need to calculate the maximum moment M about the heel. So from heel we need to calculate. So for that there are two shape of pressure distribution you can see on this bottom of the cleat. One is triangle which is from the x distance. Another one is rectangular which is having the dimension of r plus t. So we need to add these two moment pressure diagram. So anyway that length we can consider as 1 mm. So the moment per mm of span of the cleat we need to consider here first. So we know that 1.19 Fc is the vertical dimension of this pressure diagram here. X by 2 is as it is a triangle, we need to consider half into BH. So we know that X is the triangle width direction. So this is a X, and we need to consider to calculate the area of the triangle half into BH. So half into X is the B and H is the 1.19 Fc. So that's why we are applying this formula as 1.19 Fc into X into half into BH. It is a triangle formula. So we need to measure this center or center of activating this triangle from the heel of the cleat angle. So from this part where the cleat and stub is connecting, that point we need to calculate the center of centroidal distance. So for that we need to add t plus r plus, as it is a triangle shape, x divided by 3 need to consider from this edge. So that is why this equation first set of moment is calculated for the triangle portion, that is area into centroidal distance from the heel. The next one is a triangle portion, so this part. So in that again this vertical dimension we need to multiply with the horizontal dimension and to the centroidal part of this portion alone, rectangle portion alone. So here that vertical part is 1.19 Fc into t plus r is a width. Again we need to multiply it with the centroidal distance, that is t plus r divided by 2 is the half of this width. So that is a centroidal point. So we need to multiply it here, the t plus r divided by 2. So likewise this formula is formed. This is a general formula based upon the shape and the pressure distribution diagram. So thus applying all the value to this formula, we are getting 28,236 Newton millimeter of moment per mm of, that is per meter per mm of length of the cleat angle. So this is a simple formation of the equation from the pressure distribution diagram. And the next one is a moment of cleat length. In this we are just going to multiply the moment per mm which is calculated based upon the pressure distribution diagram, the triangle and rectangular. We are going to multiply with that the length of the cleat angle, that is 130 mm. So applying that we are having the moment for cleat length, entire cleat length, this moment is going to distribute. So that we got. And the tension per bolt, we know that this entire cleat is going to connect with the bolts at 40 mm spacing between the bolts we had considered as 40 mm, that is 2.5 times 16 dia of the bolt, and it is connected with 4 number of bolts. So by dividing this 4 with the spacing of 40, we are getting tension per bolt as 22,942 Newton. So this Tensile stress, again we are dividing with the gross area of the bolt, 201 square mm. We are getting 114 megapascal. Shear strength we can consider direct from the check for stress in bolts for shear cases. So it is 132 megapascal, which we already calculated. Now we need to apply the combined check for tension and shear. So this is the equation. Tension stress calculated divided by tension limit stress squares plus shear stress calculated divided by limitation of shear stress square to the whole root of square. That should not be greater than 1. This value is now 0.3, which is less and safe. We can also get this equation, check for combined tension and shear, from ACI 31807 class RD7. So here in this screen PDF file you can see it is ACI 318M05, which is showing the formula which we got discussed now. And here this epsilon value varies from 1 to 2. So we can consider this 2 here. So we are getting this 0.3. Next and the final step for design of a stub and cleat is adequacy of a stub embedment. In this we are going to calculate the embedment length required for the stub for the uplift force. So we know that maximum uplift force from the structure is 636.09 kilonewton. Pull out stress of concrete we need to calculate from the ASCE 1097 class 7.5.2. So here you can see in the screen PDF file of ACE 1097. In that class 7.5.2 it is mentioned that in megapascal we need to consider the pull out strength as 0.335 root of FC. So here FC we can consider as 25 megapascal, which we are already given as an input here, and phi value we can consider 0.85. This is as per the shear connectors. Here the definition is given. The reduction factor we need to consider for shear resistant in terms of uplift. So phi equal to 0.85 we can consider here. In general there is a lot of methods to calculate this stub embedment. This method found more critical, and the pull out stress of concrete now is 0.33 into phi, where phi is 0.85 multiplied with the square root of 25 megapascal is a characteristic strength of concrete. We are getting 1.14 megapascal as the pull out stress of concrete. Perimeter of stub we need to calculate the stub angle flanges. For example, if this is an angle member, we need to calculate this side and this side, and inner side we need to calculate as a diagonal member. So 150 square into 2 square root we need to add to the perimeter of the flange. That means 150 plus 50 into 2 plus square root of, that is a diagonal or hypotenuse length we need to add. So that will be 140 into square root of 2 squares. So by this way we need to calculate the perimeter of the stub. So this excludes the cleat. We can also do accurate calculation by considering the cleat the perimeter also, but we can ignore this for our critical embedded length calculation. Finally, the depth of embedment required need to calculate based upon the maximum uplift, which is maximum uplift 636.09 kilonewton is converted into Newton by multiplying 1000, and that to be divided by the pull-out stress and the perimeter of the stub. So that 636.09 into 1000 divided by 1.40 divided by 5112, we are getting 888 mm. So we can consider 900 mm as a minimum embedment length of the stub to the foundation pedestal. So these are all the steps. So finally we had to design our stub and cleat. Thank you. Look description for more related videos and subscribe to this channel for more updates. Thank you.